Hello everyone, I'm Daniel Krupp. I'm representing the results of a team who works at Ericsson on static analysis tools. Static analysis can be used in many ways, and actually we have a project in Ericsson that uses static analysis for creating a code comprehension tool. And we also use the Clang infrastructure for code instrumentation. But in this talk, I will talk about using the Clang static analysis tools to defect finding and to locating defects, potential programming bugs. Why we use, or many companies use actually static analysis to detect defects is that it's good. It's extending testing quite well because it can detect problems like badly indexing an array or bad memory allocations for which it would be expensive or to write specific test cases, and also it can catch bugs that doesn't have code coverage or test coverage because it can analyze the program without running it. So why we have chosen Clang and why we work with it is that we started in 2013 with Clang Static Analyzer, and we recognized that it's a very impressive checker framework. You can implement path-sensitive checkers in it, and so we started off by implementing some proprietary checkers that are checking, for example, the usage, the transaction usage in our proprietary database. So, for example, you can write a checker that can check whether a transaction is not committed 2 times. Okay, we implemented some checkers, but when we started to roll out the Clang static analysis toolset to the users, actually we got some feedback that it's not really there are some usability issues, and this talk will be about what the usability issues are and how we try to address them, and we would like to publish these improvements to the community so everybody could use it. Okay, first let's do a very short introduction of the static analysis and defect location. What are the checking techniques that are widespread in the tools? First, I could say the most simple is the text pattern matching type of checker. Those was introduced, or that is represented by CPP check. CPP check implements this, so you can write checkers that can match strings in the source code. Next, more deep analysis are AST matchers that work on the abstract syntax tree, and that enables you to do more deep analysis because you can reason about the types, for example, in your code. You can write checkers on the abstract syntax tree. And the next level of analysis would be symbolic execution. That is actually a path-sensitive analysis. It executes, it does a simulated execution of your software, but it prunes down the impossible parts of the execution. It also symbolizes values, variable values and memory regions with symbols, and also keeps track of constraints on these values. Coverity static analyzer and Clang static analyzer falls into this category. How we can actually measure the precision of our checkers, the quality of them. First, I would say would be the false positive rate. That means how many false reports you get for that checker divided by all reports. Actually, if you have many false positives for a checker, so if it shows you a problem which is not a problem in real, then it's very time consuming for a designer to just cherry pick the real hits, so it's not really useful. However, the other measure would be the false negative rate, which are the non-reported defects of all existing defects, divided by all existing defects. Why you have false negative? Because maybe you cannot reason about certain properties of the code. The lower these values are, the better. So if a checker is pessimistic, then it will have a high false positive rate. However, if it's too optimistic, it will have a high false negative rate. So actually, you cannot, the goal is to drive these two rates low, but theoretically and also in practice, this proves to be very, very difficult sometimes. Why? Because sometimes you cannot reason about the properties of a function that is implemented in an external library, or the function that the calls ends up in has a complex recursion or loop. So you cannot reason about it sometimes. How this, let's see some example of text pattern matching, how it works. So this is a simple, very simple test file which have some test cases, and it represents or it shows division by 0 faults. The first test, so text pattern matching, if you use this technique, then your checker might look like this. You simply search for strings that is division by 0, so per space 0. This type of checker can find the first hit, of course, and if the checker framework implements preprocessor macro expansion, then it also can find the second one. What these checker frameworks do actually before actually matching the string on the source code is they are transforming the source code to a canonical form, eliminating multiple white spaces or standardizing the parenthesis usage and so on, so that they are better found. However, this is this third test case which shows as a memory allocation problem. Here we have a double pointer, and then here we want to allocate a double memory size for this double. But here the problem is that the size of operator is used on the pointer and not on the pointed to type. So the star is missing here. But this kind of problem cannot be detected by the text pattern matching checker type, because he cannot reason about the type of the variable. So from the text pattern matching perspectives, the reds are false negatives, not found. This analysis is flow insensitive, so we can categorize it like that. Yeah, the next, sorry. Yeah, so the next type of matchers is AST matchers. This is, for example, which you can implement in Clang tidy, for example. So Clang tidy type of checkers are AST. You can implement AST matchers. Here, the matcher that you implement, you can work on the abstract syntax tree. So you're looking for a binary operator that has an operator name per, has right-hand side, which is an integer literal that equals to 0, and that will match to all these three locations. Macro expansions are handled properly. However, if we check test case 4, this is not found. So this checker type is not powerful enough to detect the case 4 and case 5. This is also flow insensitive checking, because it does not take the control flow into consideration. However, if we do symbolic execution, we have more power. In this case, when test, the checker framework does simulated execution of the code, of the function. So for example, the test here. And in the beginning, it assigns a symbolic value to B. But when we go into the switch case, and here, when we bind 4 to this variable b, then it will follow up that c will equal to 0. So this will be a division by 0 problem. And also it shows us when we do this checking the path, the actual path of the execution, and conditions, how this can be evaluated. It can also resolve this or find the problem described in test case 5, because here there's a get null call which ends up here, and since b here is true, then we return 0 here, and we divide by 0. How can he resolve this? Because the checkers in Clang static analyzer are context sensitive, so the function arguments can be passed and they are followed, actually. Okay, what can we do? What a checker can do with the 6 test case? The 6 test case divides by get input, but the get input function is not defined in this file. It is in the source file. It is implemented in another translation unit. Unfortunately, Clang static analyzer at the moment cannot follow function calls and cannot reason about function calls that are cross-translational unit. So in this case, he doesn't know anything about this function, and maybe it also can be the case that it is implemented in an external library, so we don't even have the source code of it. Okay, so shall this be reported or not? That's a good question. Actually, if the function cannot return 0, then that would be a false positive. So maybe if I run this on my code and the checker is configured so that it reports every unknown function as that the return value can be 0, then I may get a lot of false positive. So I may have introduced a configuration parameter to the checker to switch on optimistic or pessimistic. So checkers can have configuration parameters. If I set the checker to optimistic false, then it is pessimistic, which means that it will assume that this can be 0, so it can be a division by 0. How else? What is the other way I can help the checker? I can also assign an annotation to a function to help the resolution framework to reason about the properties. This here, as an example, you can use the GCC attribute marking, and here you mark this function that not 0, so it cannot return 0. Then in this case, this will not give you a false positive. Of course, you need to annotate your functions by hand, and it only works in this case. There is another way, though, how you can reason about unknown or external functions. This possibility is called modeling. In this case, what you do is you create a very simplistic implementation of your external function like this, which the resolution framework will execute in the same way as this function implementation would be in the same translational unit. And then he can reason about that, okay, this function cannot return 0. So why we call this a model? Because it models a certain property of a complex or external function. And the certain property, the only property we are interested now in this case, is whether it can return by 0 or not.
Okay, sorry, one question there.
Yeah, sure.
Because there's quite a lot of static analysis tools, like
yes.
for example Clockwork, and how does this compare to, let's say, Clockwork?
Yeah, I don't know Clockwork, especially Clockwork, but we compared it to Coverity Prevent, and Coverity Prevent has the kind of the same power that Clang static analyzer, and it can do symbolic execution, and it supports this modeling also very well. So the
because
power of the
Clockwork can follow like functions to different translation units.
Yes. So, and also Coverity Prevent in some certain cases, it can follow function execution across translation units. That is actually a limitation in the Clang static analyzer, and there is a work package for it, or it's up to further implementation. Actually, the last addition was in this respect was this modeling, and actually you can assign very simple stub implementations for the functions as a replacement. But as far as I know, it's not quite complete yet. So it has some limitations with overloading, for example, and macros and so on. So that is the state of the art at the moment with this. So what we have done, we implemented some AST matchers, like 33, and we contributed 5 already to Clang. However, we didn't want to try to commit all the checkers at once to the community, but we would like to commit them gradually to give the time to review and ensure the quality and so on. So we created some preprocessor matchers and some symbolic execution checkers. What is the current infrastructure and how we what were the experiences? So first, how you can write checkers. You can write checkers into Clang diagnostic engine. These will be warnings emitted by the compiler. There you cannot really do path-sensitive analysis because that would slow down the compilation. So there you can do simple flow-sensitive analysis. Then you have the Clang static analyzer. There you can implement symbolic execution, so path and context-sensitive checking. And there you have the Clang tidy, where you can implement AST matchers that are flow-insensitive preprocessor matchers. And Clang tidy can invoke both the two above tools. So if we go walk a bit, these were the checkers, but if we walk a bit up to the peak and look down, let's see what are the ways leading to the building actually. So how we use this in a bigger perspective. We have Clang static analyzer on the top here, and Clang tidy below it. Actually, when we first started the tools and started to work with it, what was a problem is that the source code is here, the build system is here, and then you need to pass the compilation actions actually to the analyzers. So because the analyzers need the exec defines and include paths so the same as a compiler to properly reason about the code. However, the two tools have two different input formats. The Clang static analyzer use the scan build Python script, and it needs the CC and CXX environment variables to be overridden. So you call scan build configure, and then the CCXX environment variables needs to be overridden. However, even at Ericsson we have many build systems that don't use C and CXX environment variables, or you have a custom self-made, manually made makefile that doesn't use it. So it is not versatile enough. Clang tidy supports a JSON compilation database with the build commands and the current working directory. It's only that is stored in the JSON DB. But only CMake can give you that output. Also, our problem was with Clang SA that checkers were not configurable, so you couldn't really easily introduce a checker configuration that I showed you in the first example. And why there are two separate tools. So we decided to use Clang tidy, invoke Clang static analyzer from that. Clang tidy has checker configuration per checker, so you can introduce checker configuration options per checker. We patched Clang tidy with Clang static analyzer, so we patched the Clang static analyzer, we committed this patch, so you could configure the checkers from Clang tidy, and we created a better integration interface with the build system, which works by the LD preload technique. So we created a shared object that is put into the LD preload environment variable, and when it is loaded, it overrides the exec system call functions, and it can lock down all the GCC calls. So for example, if the original project is compiled with GCC, you can catch all GCC calls and pass them to Clang tidy. And what is the advantage of it? That it is build system independent. which means that you can use this with any build system. Actually, it doesn't matter if this is a handwritten make file or autoconf or CMake or whatever. It works on POSIX systems. So this way we got a much better build system integration than the previous solutions. However, we still had some problems. Namely that the output formats of the tools were different. So Clang SA gave HTML reports and plist XMLs. The Clang Tidy gave normal textual warnings, and it was difficult to handle them and show them to the designer inconsistently. HTML reports are not really manageable, static HTML reports, I mean, because what we have from Clang Static Analyzer is that if you have a header file and you have a bug in the header file, and that header file is included multiple times, so included by many C files, then it means that the HTML error report will be generated for every single include. And this meant that we got, when we run it, multiple time the report size was multiple times the original code size. So it was many gigabytes, so it was not really manageable. Also, you cannot really search in them. If you want to order them by priority or by module or anything like that, it's not possible. So, and also you may want different people would like to see the results in different viewers. So programmers would like to see them in IDE, while quality assurance people would like to see them in a web browser, and so on. So actually, this was the reason we introduced a report server. So actually, we take the output from the Clang Static Analyzer and Tidy in plist XML. So for that, we needed to patch the Clang Tidy to provide plist XML, and we store the results, the report results, in a report server. How many of you know what Thrift is? Some people. So okay, it's we created the report server interface in Thrift. Thrift is an interface description language defined originally by Facebook, and this allows you to define an interface which you can generate, like Orban, you can generate stubs into many languages, like Python, C, C++, Java, and we created, and then it also gives you a transport layer, a configurable transport layer, so you can do the transport of, so it's a remote procedure call definition interface, so you can transport your remote procedure calls through a binary protocol or through JSON or whatever. So we created this, we defined the API of the report server in Thrift, which allows to store all the results in the report server in a database. It allowed also us to create a web service interface which can be easily used from a browser, from JavaScript, for example. And then you get filterable and orderable report listings. So for example, you would like to see the top priority problems in your project. So for example, if you run the static analysis on a project with 10 million lines of code and it finds 1,000 hits, then you can easily filter for a module or order them by priority and so on. This was missing from the existing toolset. Also, it is very important sometimes that you would only like to see the new faults. So if you implement it, you have a big legacy project with many hundreds of faults. Maybe you are only interested what is the new fault introduced in a development cycle, okay? And then this is called diff view. And the diff view ability is to show only the new problems or show the resolved problems. For that, actually, you need to assign hash values to the reported problems. Another problem we had with the existing toolset was that, of course, the checkers can report false positives. So there are many cases when the reported problem is not really a problem. You want to suppress it, and then in the next, you want this suppression to be preserved when you check the results again. So if it is a false positive, you suppress it, and then even if somebody writes something on the top of the file and the result report is shifting down in the file, so the location of the bug is shifting down in the file, even then you would like to identify that it is the same problem and you don't want it to be reappearing. And for that, you need the same hashing mechanism. So actually, you need to uniquely identify a problem location independently. This is a tricky problem. Actually, we have a solution for it, but I think it could be improved.
By the way, there's also an issue with that, because if you have a false problem,
Yeah.
and you mark it as that, and
Yeah.
later on it becomes a real problem, how do you differentiate?
Yeah, that is, the key to this is, for example, if you generate the hash from the bug path, so if you include every semantic information to that hash, for example, you have bug path in case of sensitive analysis, and if anything changes along the bug path, so for example, it's a division by 0, and then in the next iteration, something else is causing the division by 0, that the bug path will be different, so the hash will be different. So exactly this is the problem here, the key problem here, to include every semantic information in the hash that is relevant to the bug. And then if you have this thrift interface, then it's very easy to write clients that can fetch the reports per run. So on this interface, you can imagine functions like create a run, add a report to a run, and so on, or fetch them, or reports for a run, or filter them. Of course, another requirement is that you may want the git commit, for example, to be to not happen in case the Clang static analyzer toolset finds any problem. So this is also a possibility to interface it with version commit. So we created an Eclipse client to view the problems and to show the designer the problems in real time, and a web browser based, and you can integrate it to version commit system. Okay. And then let's see a very quick demo of how it looks like to get a feeling. Well, I'm here. I don't see that. Okay. I don't know how can I put it into full screen. Ah. Yeah. Okay, so let's first stop the server that is running and clean up the demo stuff, and demo clean, and I will do a demo check. In this example, I will show you that we have a very simple tiny XML as an example consisting of 3 files, and we have some bugs injected to it. We will run the analysis on it. We will do we will solve some of the problems and introduce one other problem, and then we will see how we can compare the check result with each other. So it is processing build action 2 now. It will finish very soon, in 5 seconds or so, I hope. Yeah, analysis is finished, so we can now run the viewer server, starting out the database. It takes some time. In the meantime, I can recheck. So this is the standalone viewer that we have. And now it appeared. So the number of bugs that we found is 3. So I can click on the run. This is the run identifier. So we have three problems in the code. first problem is at line 222, and it says that the class member is uninitialized. What is it? It says that the class member pool was left uninitialized. What it means is that if I check what pool is, it's defined somewhere here. It is a template parameter, and it's an array. If the T is a complex structure, then we can say that by this it will be initialized, so the constructor will be called. So let's say, for the sake of the example, that I suppress this bug because it's a false positive. So elements are initialized. Okay, suppress the bug, and then if I go back to run overview, then this disappeared. So there is another bug, division by 0. I click on it, and it shows me the bug path very well. So the length was assigned 0, and then I do here a printf, a division by 0 in this printf. So I can go back in the code and fix it. Not this one, the other one. Okay, so I very quickly fix it, save it, and let's say, for the sake of example, that I introduce another problem. Here, what I will do is that this function returns by a car pointer. I will copy the return value to a locally initialized variable and return with the address of the local variable, which will, of course, cause a problem. Fantastic. So then I can rerun the analysis. So I do, I do move check, and it's processing build action 1, and the 2 is the longest one. In the meantime, I show you the documentation. Yes, I forgot to mention in the presentation, I left it out, that it's very important to have a proper documentation for the checkers. As currently in the Clang static analyzer, we don't have a good documentation for the checkers, which means that if a designer, a programmer sees a hit, he cannot really understand what the root cause of the problem is and how he could fix it. So if I check the suppressed faults, this is one of our checkers that we implemented. Then if you click here, then it brings up the documentation, which is a Doxygen written documentation of the checker. And we think that it should be over? Almost. Okay. And we think that all the checkers should have a documentation which is something like this, describing the purpose of the checker, hints to fix, annotations that can be used for the checkers that I mentioned, configuration variables to the checkers, and also any possible models that the checker can use. And now if you go back to the browser for a second, how can I? Sorry, and the screen resolution is not perfect here. Oh, I closed Firefox. Maybe I can start it again. Okay, so then we see that the checker ran for the second time, and the number of bugs it found is again 2. If I click on it, then I see the result, but I can do a diff view, so get diff, which means that I can list the new problems only. The new problem is only the address of stack memory associated with a local variable. If I click on it, I can see the problem which I introduced just a minute ago. If I go back to diff overview, I can see the resolved bugs like this, the division by 0, which I fixed, and I can see the unresolved bugs and suppressed bugs. So the suppressed and unresolved bugs, which was the member initialization problem. And so it concludes my presentation, which is that we would like to introduce this tooling as an open source project, so everybody can make use of it, and we think that this way you can use Clang Static Analyzer and Clang Tidy in a more efficient way. So thank you for your presentation.